Okay, welcome to the NUPOC Video Study Guide number 18. Let's look at question 15 in the General Math section of Guide 1, which asks us very directly, what is a logarithm? So a logarithm is just an operator that returns the power to which we would have to raise its base to get the result, that is the input, to the logarithm. So let's write it out in sort of a mathematical form and see what that looks like. So say we have some value x and it's equal to some constant a raised to the y. Okay? So what the logarithm gives us is it will return y. It will return the power to which we have to raise its base, so this is log base a, to get the result that is the input to the logarithm. Right? So if this were, say, 10 squared, we know 10 squared equals 100. So if we, there should be an equal sign there, of course. If we wanted to know what log base 10 of 100 is, it would be the power to which we would have to raise the base 10 in order to get the input to the logarithm here, or the argument of the logarithm, which is 100. So what power do we have to raise 10 to get 100? Well, that's easy, just 2. Right? And of course another popular logarithm base is e, or the natural logarithm. So for that, for example, if we had e to, I don't know, let's say the 2.5, e to 2.5, let's say that, equals some value x. I don't know what that equals off the top of my head, but let's just say it equals x. So if we have the natural log ln of x, guess what that would return? It would return the power to which we would have to raise e, the power to which we would have to raise e in order to get this x. So what's that power? 2.5. Now if you're following along with the solution manual to this study guide, you'll see that for this solution they kind of give a more rigorous math definition, and I'm just going to touch on a couple points that they list there. So number one is the input to the logarithm, or its argument x. X has to be between 0 and positive infinity. It can't be less than 0. That doesn't really make any sense. How would you, if you have some a here, some constant a, what could you raise it to get a negative number here? Nothing. If y is a large number, then x will be a large number. If it's a large positive number, x will be a large positive number. If y is less than 1, then this x will be less than a. It will be some root of a. And if y is, say, a large negative number, then this will just be a very small number, like 0.0000 something, right? So that's one thing. But we can also say, however, like we were just discussing, that the output of the logarithm, the power that we have to raise the base to get x, y, that can go from minus infinity to plus infinity. Because again, think about it. We could have minus a very big number here, and x would just be very small. We could have a very large number here, and x would be very big. So x is bounded between 0 and plus infinity, but y can go from minus infinity to plus infinity. Or how they write it in the solution, they say y is just the set of all real numbers, and x is the set of all real numbers between these boundaries. One other property that we can say about all logarithms is that log base a of 1, right? Log base a of 1 is always, I'll write it on this side, is always 0, right? Because anything raised to the 0 power is 1. Even 0, actually, which we'll see in a problem coming up. So anything, so what power will we have to raise any base to in order to get 1? Well, that's 0. So this is common for any base a. And let's just look quickly at what a graph would look like. and what a couple different graphs would look like of logarithmic functions, right? So let's say here this is our y and this is our x, okay? So we know that all the logarithms, when x equals 1, our y is going to equal 0. So so this is x equals 1, okay? And we know that we can never, our x can never go below 0, so we're going to approach this axis asymptotically. And as our x approaches 0, as x approaches 0, as this becomes a very small number, that means y is becoming a very large negative number, so it heads off in this direction asymptotically. And as x is growing, we know that y must be becoming a large number, though not necessarily as fast as x, especially as y becomes greater than 1. So we're heading off in this direction. So the curve sort of looks like this. Okay? So let's say that this is our log base 10 of x. Okay? So how would ln of x compare to that? Well, e, the base of the natural logarithm, is a smaller number than 10. So for a given value of x, right, for a given value of x here, for a given result of this a to the y, we have to have a larger y because we have a smaller a, right? So our y, or the power we'd have to raise e to, is going to be larger, right? So it's going to be somewhere up here. And then as we come down and x becomes less than 1, right, we're going to need a larger negative y to get to the same value of x. I mean, think about that, right? So if y was minus 1, or let's just say x is 0.1, let's do it over here. So if x were to equal 0.1, right, well, that's just 10 to the minus 1. So our y would equal minus 1 in the base 10 case. But if x equals 0.1, I mean, let's look, what would e to the minus 1 be? Well, that's just 1 over like 2.7 about, right? 2.71, whatever. That's not even close to 0.1. I mean, that's less than, or it's still greater than 0.3, right? And so, well, what about, e to the minus 2? Okay, well, that's like 1 over 2.71 squared, so that's, I mean, even if we rounded e up to 3, it would still be 1/9. So we're still not quite there. So we need a larger number, a larger exponent on a larger negative exponent on the natural logarithm to get to the same value of x. So what a given value of x here, we're going to have a larger negative value. So ln is going to look maybe something like this. So this curve here would be ln of x. So that's pretty much it. Logarithms are just operators that return the power you would have to raise its base to get the result that is the input to the logarithm. Two popular bases are 10 and e, and this is what they would look like and how they would compare if you graphed them.